before that, if Dr. Abhishek and Dr. Amit, do you want to say something?
We can go ahead. We can go ahead.
Really late, so maybe we can. And please type
Yes,
the
ma'am. We can
question
go
and
ahead,
answer.
ma'am.
Yes, thank you.
Yes, thank
So
you, ma'am.
please type your whatever questions, comments in the chat box, which we'll take after the talk. Priyanka, please.
Thank you. Thank you, ma'am. So today the topic is advances in orthotics, and it was a little difficult because there's so many advances. As I got to know, it was a great learning experience for me also. So if we start with all the basic ones, it will become never ending to reach the advanced. So we'll just talk about a bit of the principles of the basics and mainly an overview of the advanced. But the advanced ones have a lot of engineering. It's mainly in all the engineering journals. So let's see how much we can grasp out of that. So what are the advances is that the orthotics, they're advanced because now earlier they were purely passive devices meant for supporting. Okay, from there now it has come to now either just to, they were passive support for active and functional and customized devices, but now it has become more dynamic, more functional, more customized to enhance mobility, stability, and become energy efficient also. And therefore, individuals with neurological musculoskeletal impairment, therefore elderly also, they are in fact being used for able-bodied persons, for athletes also in a way. They are being used in the army. So when I went through the journals, I found out that they're being used for beyond rehabilitation, they're being used to enhance function. So there's a lot of interest in this field. And the next generation orthoses incorporate advanced materials, technology, and smart mechanisms to improve user compliance and clinical outcomes. So what are these advances? Mainly there is the printing technology in terms of 3D printing, in terms of the designing to make it more personalized, precise, lightweight, and cost effective as well. And they give you a better fit and they give you lesser pressure points. And they're advanced materials. So like thermoplastics and carbon fiber, they're lightweight, they're non-toxic, and they're more comfortable as well as being strong. And they reduce fatigue also, especially for elderly. Also, they're smart because they are sensor based. So that's what they integrate sensors like myoelectric or pressure sensors, and they give a real time monitoring, feedback, and adaptive support, especially in the lower limbs. So lower limbs are much more advanced for the gait, and upper limb is a little more difficult because of all the finer functions and sensory proprioception which is required. So lower limb has much more advances that I was able to find. Also, neural interfaces. So there is an emerging technology for brain signals to be used or muscle activity to control the orthosis, and this mimics the natural movements for better function. And also topologically optimized, which means that computer-aided designs. They create structures with maximum strength and minimum material. So they're very efficient devices. What are the benefits? Why are we being used? Is that they improve gait efficiency, metabolic cost, which is the main thing for energy cost goes down. They enhance functionality. So increase walking speed and navigation is better over hurdles, over obstacles in crowds. They're more comfortable, low weight, customized. So less fatigue, so increased compliance. And they support neuroplasticity as well, which is the one of the biggest keys, which is that they're able to perform more natural repetitive movements, and this helps in natural neuro recovery as well. So it's good for early neuro rehab. And advanced orthoses are crucial tools for rehab, especially for improving, as we know, quality of life, independence, and all the complex mobility issues. So existing orthoses, we look at it not from the classification and the point of view we already have, just a basic overview over the principles and prescriptions maybe. So what is the ankle foot orthosis? We'll start with that. We know the journey coming from the mechanical AFO to the plastic AFOs to the very lightweight AFOs. We know there's a solid AFO, then there is a hinged AFO, ground reaction force, posterior leaf spring AFO. So one of the ones which maybe once students were discussing, they wanted to know more about the ground reaction force AFO. So we know every action has an equal and opposite reaction. So the force coming from the body weight to the floor exerts a similar force from the floor to the body weight. So that is why this is colloquially, this is just called informally as the floor reaction orthosis, AFO, because the extended rigid forefoot section it gives an extension, a knee extension moment at mid stance, and it prevents the tibial collapse. Okay, if your gastrosoleus is weak, so it gives knee more stability. So in our institute, we also make it like this. It's an anterior shell AFO. So it gives knee flexion control, can also give hyperextension control. It also gives mediolateral ankle control. Okay, then when we look at the prescriptions, which are the usual ones. So there's mild foot drop, for which we have the posterior leaf spring AFO. Then if we want a little more, if there's moderate foot drop, we can use with a plantar flexion or dorsiflexion assist or stops. Then if there is also the weakness of both dorsi and plantar flexors, then we need hip and knee extension movements also, because we need higher control. And if there's only spasticity we're looking at, then we look at a rigid ankle foot AFO. So now when we talk about the advanced ones, these are usually called the AAFOs, which are the advanced AFOs. What do they offer? They offer multiple degrees of freedom. So they're looking at mimicking the natural degrees of freedom in all the planes that we have in the ankle. So these are, one on the right side is actually an exoskeleton, which is like a robotic one, and the other one has a pneumatic muscle. So we look at it, it's very technical and very engineering quality, but so it's not really in medical terms of indications and contraindications that I'm able to explain, or advantages, disadvantages, because they're all in terms of, right now, they're all in the initial stages. They've not all had approvals, and they've not all had any explanation of which one works better. So looking at the carbon fiber AFLs, we know they're lightweight, durable, and they also have a bit of energy storage compared to the traditional plastics. They can provide dorsiflexion assistance for swing, and there's also dual carbon fiber, which gives dorsiflexion and plantar flexion, both energy storing device. Then we have a dynamic AFO. This also assists with the toe off, because here even more energy is stored. There's a clamshell, anterior shell, that also helps to offload the ankle and foot. So that can be used for soft tissue relief also. And this is made of very lightweight material, as well as and titanium alloy. So this also assists and gives a more natural gait and reduces the metabolic cost of walking. Then there are oil dampener AFOs. So dampeners are there in very old-fashioned ways also, and then made in very advanced ways also. So there are cylinders which give resistance against plantar flexion, and that this is for, like, if the foot slaps, this improves great gait mobility. So we see it as a bar. We can see it as a small dampener to a big dampener. We can see it as a posterior bar, or it can be a small dampener which basically resists the movement. Then, of course, we've all heard about the 3D printing. The 3D printing AFOs, 3D printing is also called additive manufacturing, because it's not where we get a mold and then we make something out of the mold. It's because we get a picture, we scan a picture, and then we keep adding things onto it. We add the material to make the AFO or whatever we are trying to make. So this is also very precise, very customized. Relatively rapid, is actually not very rapid, but it's based on 3D scanning. So this allows for complex, personalized, and very lightweight devices which are very comfortable and user acceptable. So a little bit about additive manufacturing or the 3D printing. This is how it works. In the blue in the block, you can see the material comes as a material is being laid out by the heater element, which has a nozzle, and that keeps laying it out in layers. So according to the design, if we look at the left, the long panel which is there, which is comparing how the normal, usual positive and negative negative and positive mold that we take, and the other way we take a 3D scan. Then on the computer, we convert it into a modified geometry. And then according to that, automatically the elements get added. Additively, it gets added, and an orthosis is made and fitted on the patient. Of course, disadvantage if it stops or if there's a slight mistake and everything goes waste, and it does take quite a bit of time. But overall, it is really very good. And then there are also other innovative designs. These are two of them in the market, AF Servo and Turbo Men, which are externally attached to the shoes, and they provide freedom from skin contact with the brace. They allow for easy and more comfortable use. So not much about them. I found this just from their own websites, that these are also there, which assist the shoe in picking it up. Then some articles were about the mechanical designs. These were, again, as we can see, it's from the Bioengineering and Biotechnology Journal. So it's complicated terminology. but they've explained them as passive airfoils, which are basically, they have only passive elements like dampeners that we spoke about, or resistive forces, which restrict the motion, or they have springs, which increase, which release the motion. So the basis on the mechanical storage and release of energy is the passive airfoils. Then quasi-passive or semi-active advanced airfoils, in which computer control or small motors are there to adjust the performance of the passive element. So the dampeners and springs are controlled by the computer or a motor. And then completely active advanced airfoils, which are the robotic exoskeletons. We'll talk about that more in detail later. And they have what you call actuators. So the whole word actuators is everywhere, because actuators is what converts things into motion. So it is by a hydraulic activator, a pneumonic activator. So it's a lot of physics in which how you convert energy into motion in the human body. So it's always connected to a power source, and it uses the force, assistive forces, to create motion. So this slide is complicated. So, but just to give a view, there's a classification for these AAFOs, but this is not really for medical usage. It's mainly for the mechanical purpose. That how the springs are there. The springs are there to create a torque. There are resistive passive springs which are there. Then there are angle dependent, okay, cam-cat dependent resistive for springs which are there. Then a spring can be there along with a clutch. Then an electronically controlled clutch can be there with an energy storage element. And then there can be a rotatory motor, which is there. And there can also be torsional forces, which are used, and traction forces, and so on. So explaining it is a little difficult because this is all that was available. But yes, we can see how they are not the normal AFOs where we're using a plantar stop and a dorsiflexion assist. These are more complicated devices using a lot of rotatory motion and a lot of translatory motion to create, mimic the natural human gait. Then FES, we know that FES is being used. So these are called the neuroprosthetics, which are being used in conjunction with either it can be used along with the traditional orthosis, or it can be used by itself also. So mainly in independent ampulators where there's no contracture, but there's foot drop. So here, like these devices are there where you directly, without an orthosis also, you can put it on, and it constantly detects the muscle movement to activate the walk mode and prevents the foot drop. And there's a constant monitoring of the EMG parameters, and which helps in the patient to prevent them from getting fatigued. So now coming to the knee ankle foot orthosis. So that was all about mainly the foot control devices. Now coming from the knee ones. So we know these are our conventional ones, then the plastic ones, then some the mechanical ones, which are with advanced materials, but it's also still a mechanical modular one, KFOs. And then we have the ultra modern ones, or the highly advanced ones, which have all robotic elements in them. So the conventional metallic one, which has metallic elements, the modular plastic ones, separate modular units, which can be changed also. And then the advanced ones, mainly the advanced ones are the stance or the stride controlled KFOs. So they're made of premium materials, and they have very superior locks, which are very precise, and they can also be controlled by the computer. So in the advanced KFOs and the complex devices, the stance control KFOs, or the SCOs as they're called, they automatically lock the knee joint in extension during the stance phase. So this allows but it allows for flexion during the swing phase and promotes a natural gait and reduces energy expenditure. Then, so this is what the other one does as well, but how it does is, this is done through the computer, this lock. So, and then the reciprocating gait orthoses, they are there for a long time, but I don't think we are using them as much. They are, even the basic RGOs are there for a long time, which are now being, they're the specialized HKFOs. So we'll start from the beginning, because I don't think we have discussed this much. So they allow for a more natural and alternating stepping pattern. So it's a reciprocating gait, like the human gait. It enables functional ambulation in paraplegia or neuromuscular disorders. Sorry, okay, this was supposed to come earlier. This is the same stance controlled KFO. HKFO. Okay, yes. So these are the KFOs. When we HKFOs, when we look at the conventional design, then we have the conventional design, and we have the hip control design. Then we have, there's something on my screen, I'm so sorry. So we come to the reciprocating gait one, which unlike other HKFOs, they're not two separate HKFOs. I mean, this HKFOs are the RGO. It creates a dynamic motion for ambulation. And this is done for ambulation. The torso instability that is created by the non-working hip extensors prevents secure upright posture, even when the legs are braced. So this has a molded pelvic band. This has bilateral hip joints, offset knee joints, posterior thigh shells, all. And then it also has molded bilateral AFOs with carbon fibers in the modern ones. But it could also be made with the regular ones. And the main differentiation is that there is a cable connecting the two hip joints. Okay, so prior to the RGO, it was not possible to be upright without the use of hands for high-level injuries. This forced the patient to ambulate using energy-consuming swing to or swing through gait. We've studied that. So it is the only device that allows for hand freestanding without immobilization of hips. Okay, this is done by a linked torso. So without going into much of the details, I'll just explain the reciprocating gait because there is a specialized bilateral hip, knee, ankle, foot orthosis, which gives contralateral hip extension and ipsilateral hip flexion. So this is what it does. Contralateral hip extension and ipsilateral hip flexion. So the principle of reciprocating gait is that it's a form of walking in which one leg is placed sequentially in front of the other, like normal walking, and it enables patients to take the body weight through the stance leg. Whereas in the swing to gait, it effectively means that both the legs are forward at the same time and the hands take all the weight. So this is highly energy consuming. And while this is gives the hands free as well. So from a development point of view, we know that the patient there are non-working hip extensors in the upper body, what we call as jackknifing, when the upper body falls uncontrollably forward. And only with some forces can this torso be stabilized and hands are freed. So what is that? So in non-RGO bracing, the patient's hands are tied up, because we are using something for hand support. So for supporting the torso, and they are not being able to use them for activities for functional exploration. In the RGO, this supports the patient without using the hands. So it is completely on the brace itself. And with the use of an RGO's reciprocal mechanism or a three-way linkage, the right leg and the other leg in the torso, where the flexion of one side causes extension of the other while the torso remains vertical. So that one of the main components, without going into all the components, but there is the pelvic band, which is very different. So there are many kinds. The initial design had a hooked cable design, then came a vertical cable design, then a rocker bar came, and then finally a center for orthotics design in which a rocker bar pelvic section. So this rocker bar, like we have in the rocker bottom sole, helps in easier movement, helps in translation movement. Then the other parts, I'm not discussing the linkages and the joints, but the AFOs are also made of smart materials. So you can also use simple solid ankle foot AFOs. You can have articulated AFOs, or you can have an anterior shell or the floor reaction AFOs of the ankle foot complex, as well as the knee, and this does not impinge on the soft tissues in the sitting position. So that is the main thing. This also allows the patient to sit without taking off the orthosis. So there are many types. There is a Louisiana State one initially. Then there was forgot the intelligent reciprocating gait, and the third one is the advanced reciprocating gait. So that's the one we are on now. So, and there can also be powered devices because I'm not able to see my own screen. So the powered devices, they can also, these RGOs have also now become powered, from the basic RGOs to the hybrid devices, which comprise the mechanical orthosis with FES. It can also be a pure FES system, or it can be powered, as in robotic. So this FES, we know, of the quadriceps and hamstrings in conjunction with the RGO in paraplegics can achieve a continuous walking speed of about 1/3 to half of the normal. Then in advanced AFOs, They can use a powered orthosis with a small direct current, a hybrid neuroprosthesis, which has an FES stimulation via implanted intramuscular electrodes. They can be an energy storing orthosis where also the AFOs are energy storing. And they can be, it causes a pneumatic fluid buildup. It can capture the excess energy during quadriceps stimulation, transfers it to the hip, and releases at an appropriate time to achieve hip extension. So there were many, many more, which I could not clearly understand, but there were many more advances in the RGOs, which were highly complicated and at the very early stage. So, but we can see that they have a lot of wires. That's why, because they're all in the early stage. Even with the FES, lot of the neuromuscular control. And on the top, we can see for children, we have the more basic RGOs, which do very well for the children who want their hands to be free and who are able to play and sit and also have very colorful and very acceptable orthosis, lightweight for them. So for them, the simpler ones, and for adults, possibly the more complicated ones are being looked into. So we also have very early, we can see the swivel walker also has, this is the basic swivel walker when it started, where it was being used without using the reciprocating pattern for in a walker form, and where the child can sit also and do transfers also wearing it. So that also has an advanced version now with more lightweight materials and mechanisms, where, as you can see, the child on the right side needs so much of upper limbs are used, and the knee joints and all the joints, hip joints, they have to be opened all the time to be sitting or changing position. Whereas in this walker, the child is much more independent. There's also the parapodium. This was the initial design, which was again slightly different from the walker, because this is not a swivel board. It's mainly like a standing frame. So, but this also allows the child to sit and has the hands free. So this also has very modern version, and also for adults, where the swivel board, but this parapodium standing frame can also be used to make movements with actuators and with computer aided control. So then coming to the exoskeletons, these are biomechatronic devices you couple to the person's body. It's a wearable robot. So exoskeletons are a structural mechanism that has joints, links, and it is worn by the human user, a robot who is worn. So the whole kinematic structure performs several motions which are similar to that of the human body. And exoskeletons are devices designed to enhance human strength also. So by the external framework. Thus, these devices are currently under development for enhancements of human motor function also in the military. So that's a great, the biggest interest is in, unfortunately, warfare, but a lot of advances are also being made over there, where the military themselves are using, and also in industry to improve, automated workforce. And finally, we come to medical applications. So then we can see this is different. How is it different from a conventional orthosis? Because it has a power source and it supplements and produces the own movement. So you cannot, it's not your own movement as such. It's a programmed movement that it will be, according to your own requirements. The movements are programmed, and you can, it undergoes the movement, the movements are produced. But it is also heavy. As you can see in the picture, the motor has to be carried by the person in a backpack. So that increasingly increases the weight. So soft robotics and wearable exoskeletons, they're made up of biometric sensors so that the limbs can move along with the individual. When the user moves an arm, he or she will also move a part of the frame, and you can pick up an object, move it around, do whatever you want. In some cases, only armor is provided, which only gives strength, not movement. So it can be used as a simple supportive structure also for minimizing fatigue, for preventing overexertion and injury, while some are also built for capacity for movement, like we know in our paraplegics, and the operator can move without limitations or with much less limitations. So DWalk is the device that we commonly see in most of our conferences. So what is that? That is comprised of a motorized exoskeleton, that's your whole robotic unit, and a battery unit, and it's a computer-based controller. This is all in the backpack, and a wireless mode sensor, and an array of wireless mode selector, and an array of sensors. This measures the upper body tilt angles, all your joint angles, ground contact. And there is a built-in backup system for both the battery and the main computer. So the exoskeleton has bilateral lateral uprights for the thigh and the leg. There are hinged knee joints and articulated to foot plates distally, and also a sacral band. So that is all that I could understand. A lot of more complexities, but these are just actually some of the devices, but there are a multitude of devices. So, but not possible to cover everything because we also have to go to the upper limb advanced orthosis. So upper limb, again, just the basic considerations, anatomical and biomechanical considerations, which we need in whether it is a conventional simple one or an advanced one. The wrist is the keystone for hand positioning. Neutral positioning of the wrist or slight extension is required for optimal hand movement. And the MCP joint is the key for the finger function. And when MCP joints are hyperextended, the IP joints flex. Okay, this is how the natural tenodesis reciprocating action happens in the hand also. And extension stability of the wrist is important for optimal functioning of the hand. That's why most of even our resting splints are given in a bit of extension. The wrist should also be placed in slight extension to maintain flexor tendon length and to improve hand function. So we know this is the intrinsic plus position, okay, where we have an MCP flexion, IP extension, slight wrist flexion. This preserves the anatomical arches of the hand, opposes a claw hand. So claw hand is the least useful functional hand. We don't want that. So even in a flail limb, or not flail, but even in a completely immobile hand also, sometimes this claw hand position can come because of imbalance of these musculature. This position is also referred to as the safe or intrinsic plus because the intrinsic muscles of the hand are the weaker ones than the extrinsic flexors. And these motions, they're difficult to obtain. So we want to promote the intrinsic MCP flexion and IP extension. So we also use this in a tenodesis splint. We know the basic one, which we use for our spinal cord injury, C6 level, where we can use the wrist functional, the wrist flexion is there, extension is there, and this produces a controlled passive flexion of the fingers to produce a three-jaw chuck, okay? And then it also helps in it creates a release. So this is where, and then looking at just grossly going over how do we look at the splints. There is a static, the splints can be static in nature, where it immobilizes the joints. It can be static progressive, where it is in an immobile position, but it's adjustable immobile position, commonly used in post-op conditions. It can be dynamic, like one component is static and there's one component which is dynamic, like we have the out triggers, where we want to strengthen the part which is still working, okay, like in our wrist drop splints. And then we have a stereo static splint where we want to increase the range of motion and we keep increasing the static splint range. Okay, so it can have, like here, this is the one which we use when we have a wrist drop. We can use it in without out triggers. Or if we want to strengthen the flexors, we can also use it with the dynamic out triggers. So they can be static or dynamic splints. They are named according to the joints they cover. They also have common names. There are various nomenclature, but we won't go into that because we talk about the advances a bit. The similar advances, again, there is 3D printing, which is 3D printing is also being used with robotic devices and on their own. So this is there. Then there's also myoelectric. Again, that is big. It's also being used for stroke. Okay, it's also being used to overcome spasticity, where it is, I can't see the wearable system uses surface EMG from the affected muscles, controls the powered orthosis. So now we have a powered orthosis also along with the EMG. This gives powered assistance for elbow flexion extension, gross brass motions via motors attached to the exterior of the brace. Functions by continuously monitoring the surface EMG of the user's biceps, triceps for elbow motion, and the forearm flexor extension for grasp. These signals are filtered and processed to provide desired joint torque. Okay, the torque is the moment which creates the movements. Okay, the desired movements and proportional to the exerted force. Okay, how a little active motion is from the user and this device supplements the rest of the force. So then this is also hand extension robotic device, which is for stroke. So a lot of devices for stroke with severe impairment, where a robotic hand glove is now being used. We have seen our usual robotic devices, but now this is a hand glove, which has a lot of actuators, a lot of cable ties in them. It has a battery pack, microcontroller, and there are also buttons to control the modes. Okay, it can be worn like a batting glove, and it has separate cable ties for each of the tendons. And usually you can do an open palm design. So this extends and it can help in flexion and extension, grasp and release easily. So this is in a developmental stage, as it is written, development and testing with severe hand function. So this is what was found. that with a few 5-stroke survivors, they are able to achieve, grasping a bottle and even fine movement of grasping these blocks. And then there is a script passive orthosis. There must be multiple names. There are multiple names. I have just picked a few where this is an interactive hand and wrist exoskeleton for rehab at home. So this is also being under the developmental stage where it's a passive orthosis, but right now none of them are open for going for home, but this is for home tele rehab that they're trying to have this script device where you can have a robotic sensor and be controlled by the person somewhere else, and you're having this exercises at home. So multiple finger movements, individually, active or passively based. It's still in the developmental stage, and as you can see, it has a lot of. It's mechanically very complicated. It has. I could not really understand how to explain, but there are a lot of spring mechanisms. There are a lot of actuators which are there, and it is it's controlled with a lot of from the computer, basically computer programming. Then there are also dynamic hand orthosis for recovery. Again, in stroke, there has been a lot of the recent advances. So here, dynamic hand orthosis, again, similar. Glove is there inside a wrist splint. So a splint attached to a glove, okay, and bands offer extensor assistance. Okay, this increases hand opening. So when grasp is there but release is not there, improves access to rehab activities. Then 3D printing, then low cost hand and finger wrist orthosis, especially for children. 3D printing, children accept very well because they are highly customized and very colorful. You can make them, and plus they're very lightweight. So, and plus taking and donning and doffing is also very easy. So the way to do it is you have to take a mold, and from that, again, the CAD/CAM is being used, computer aided design is being used, and then by that additive manufacturing, there are actually 2-3 ways of manufacturing it, but they're all additive. So in which you can have these kind of splints, and they've tested it against the usual splints. There's no consensus which one is better, but at least it's not worse. It does work. So they have been working well. Then again, creating that along with a robotic device in an exoskeleton, using it along with out triggers, using it along with sensing modules. These are all under in the process of being made, and also by increasing ventilation of the hand. And also you want to free the hand for proprioception. So you want to have as less material on the hand as possible. So all that is being under study. And then these are some of the same designs which are being made in 3D printing, actually, the basic design in this 3D printing. So the Anna deviation, then one is there. This is the black one is it's a smart one which can be used, which is like a static progressive one for using for different ranges of motion. There's a torsion spring in this joint to support extension, and it can be activated and deactivated, while you're donning and doffing. So the position of the wrist can be changed. Then again, this one with the out triggers, which has a static component and the dynamic component. So this splint is similar way, but it is done in a smart fashion, as in using smart devices. Then you have devices for active finger movement for the CNS disorders. They have closed tips of the fingers. They allow the force to be transferred without sliding the glove across the finger. So you have some of the fingers free also. Okay, and pressure sensors are there to detect the intention of hand closing. Then the last one is a robotic glove. For the support of the hand function after stroke and hand injuries, fingers can be mobilized into flexion and extension. So it's a rigid glove and actuated joints. The actuated joints are those actuators are present on them, and palmar side is free for grasping, and the splint is attached to the forearm and foretips. Then there's a system to facilitate donning and doffing. Actuators are integrated on the forearm part, and the weight shifts are there, and it's also controlled by EMG signals, and soft elements are used to decrease the weight, and the wrist is fixed, which simplifies the control. Then this is something, again, very complicated, where they are using or very smart, where they're developing a robotic hand orthosis for finger flexion motion with surface EMG. Now this is a prototype. These are all prototypes, as in they're just making, it's all in the design part. They're all in the lab right now. Then they're being tested on very few. Like even in our institute for research, we have had 2-3 groups coming from IIT Mumbai with prototypes where they want to test. So this is a very new field, but lot of prototypes are being there in the market, even in India. So in the Western world, there are lots. So talking about the advanced, now coming to the spinal orthosis, here I could not find too much, but similar with the similar kind of advances that we have seen mainly for all the spinal deformities, where advances in spinal bracing is again in terms of mobility and actuation. Actuation is in getting more precise. So use of sensors to track the brace compliance, the interface pressures, all this can be tracked. Force distribution and torso parameter characterization. Then developments in brace construction technologies using CAD, CAM, 3D printing, smart materials. Then technology in the force and temperature sensors, as well as imaging and manufacturing methods. All these have shown great progress. But the implementation of these technologies will go a long way. So right now, none of them have been implemented, but a lot of designs are in the market. So these are the usual ones, the Milwaukee, Boston, and some more braces which are there, which are again, some are made only by CAD CAM, some are made in the traditional way. Then there's a dynamic derotating brace. A modification of the Boston brace, the second last one, okay, with aluminum brace and anti-rotating and derotating effects on the trunk for high thoracic curves. Then there is some few pictures that I could find, this Triac brace from the Netherlands, which has soft plastic and metallic connections. This is a flexible brace to improve cosmetic appearance and comfort, developed for primary curve correction and idiopathic scoliosis, and the planes of action are frontal sagittal. Then the spine core, which is there, that is an elastic brace, prefabricated one. It's again a dynamic bracing solution for scoliosis or hyperkyphosis, and it is also suitable for children from the age of 5 and for certain to 20 to 50 degree Cobb's angle. Okay, and then there is the ScolioSmart. The ScolioSmart is again like a soft suit, prefabricated elastic fiber. Then it utilizes the energy of the human body's natural movement to generate new muscle memory. This new muscle memory decreases and stabilizes asymmetrical muscle firing, thus reducing the risk of curve progression and helps the spine unravel naturally. So it is never forced. So this is using the muscles in a natural fashion. And then we have the Flexi spine, which is from Korea, which is semi-rigid and it's 3D printed, elastic, and a foldable plastic body. So it's very lightweight. It's only 4 millimeter thick, 3D printed from foldable plastic, and allows mobility and enhances exercise potential to treat scoliosis. Then many more braces, which few pictures, the Japet Atlas brace on the left side. So that is, this has this is an active brace. Active means that again, some motors will be there, or actuators or electrical signals. So 4 electrical actuators will be there. Rigid brace, mainly for pain relief and for recovery of mobility, extends the spine to release the pain actively, and adaptable system maintains complete freedom of movement without restricting muscular activity. Then the next one is the rose dynamic brace. The orange, with the orange and the metallic orange one. Here, the rose dynamic brace, again, it's an active brace. It has electric, series, and elastic actuators. It is rigid and treats scoliosis and also torso stiffness. It has a 3-point bending, push, movement, and elongation, and many other actuation mechanisms. And the plane of action is 3D, frontal, horizontal, sagittal, and according to a brace map classification also. Then there is a green sun one, the third one, which has, that's the one right on top. It's passive, but it is not active, it's passive, but it's semi-rigid, and it has elastic and metallic connections, and the segments encircling the torso. And these elastic elements require immobilization by engendering stabilizing forces. They also allow relative motion of semi-rigid segments, but real-time monitoring of the corrective process is there. So that adjusts the brace. Then we have the wraps, the last one. So that is very active. That is active series electrical actuators. It's rigid, torso, postural support. It's a parallel robotic device consisting of 2 rings over the chest and hips connected by I don't know what is this 2 UPS and RPS. It was a huge journal, but this architecture is there. And this modulates, basically what it does, it modulates the forces and the displacements applied to the torso. So whatever deforming forces are there, it actually displaces them. So it prevents further progression. So coming towards the end of the topic, where we have discussed so much about all the advanced orthosis, but despite all the advantages, of course, everything has disadvantages. We know that they are high cost, they're limited access. Not everyone can access them. They're very advanced, particularly robotic and 3D printed solutions. They're very expensive, limited availability in low and middle income like ours. And their technical challenges also and maintenance. They require specialized training, highly specialized to operate. Our normal orthotics and prosthetics training will not do. You need a lot of supplemental engineering training or bioengineering training, and they're subject to battery life constraints and require technical maintenance. They require maintenance like any of our other gadgets or automobiles. And there can be skin irritation and pressure. Despite better materials, device can still cause ulcers, pain, blisters, particularly during the initial breaking in period when you are trying to customize it. You're molding it according to your needs. And energy expenditure and weight, some such as the exoskeletons. The exoskeletons are heavy. You're carrying the entire robotic structure on yourself along with the backpack with the battery and the backup. So that is heavy, and the energy required to operate them leads to fatigue. You also need, that's why you can see them still, some of them requiring braces, requiring crutches. So, and muscular atrophy. Prolonged improper use of support devices can cause certain muscles to weaken or atrophy. They can also cause discomfort and fitting issues because achieving a perfect, comfortable, functional fit is challenging. So, unless you have a perfect fit, once it's made, it's not very easy to change and recustomize. Once it's made, whether it's 3D printing, especially 3D printing. So, the entire thing will go for a waste if it is uncomfortable, and it will have a high rejection rate. Low adherence, abandonment, up to 65% of the patients with SCI abandon orthosis, due to lack of functionality, difficulty in donning, doffing, discomfort. So we know this is a repeat of the same thing. Also, there is a high purchase and maintenance cost. Also, insurance might not cover it. In other countries where insurance covers most of their requirements, medical requirements, then there are physical limitations also of the device because of its heaviness, it's bulky, inflexible, cannot navigate narrow spaces. Then it can be a safety and health risk also. It can cause falls because of the weight or because of the fatigue it causes, and it can lead to abrasions, pressure sores, fractures, especially in patients with pre-existing bone weakness or spasticity. Then there are braces for spasticity also, but they were very difficult to for me to explain, and the pictures are not very clear, as well as picture braces which are there for CP children for their crouch. So a lot of spasticity, anti-spasticity bracing is also there using EMG and robotics. But then they themselves can also cause, in children with high spasticity, cause problems. And also operational user challenge. So there are slow gait speed, limited battery life, and the need for highly trained caregiver or operator. So all the patients might not be able to use it because of the high skill that you need to use it yourself or to update it. Technical and fitting issues, one size fits all approach is not there. So this is highly customized. It's very complex. Of adjusting the device to fit the diverse body proportion is a major challenge. So clinical limitations, lack of long-term evidence. So that right now there is no evidence for, there's no consistency that which one is superior over another, over conventional or physical therapy. So there are no, these are so many advances, but there is nothing has been proved because no one device is ready also as yet, except for the rework and some of those exoskeletons. The rest are in very early stages. Despite these drawbacks, they're valuable tools for rehabilitation, though not yet ready for widespread, unmonitored home use. So I would like to acknowledge for a lot of this, the P&O department in AIPMR, the OT department also, where some of the basic ones also put it in a concise way, they helped. And the journals which I referred to, if you're interested in learning more about the technology, mainly they are the bioengineering and biotechnology journals, biomedical engineering journals, applied sciences journals. There's one called autonomous robots, and there are this IE journal for electrical and electronic engineers for transactions on neural systems and rehabilitating engineering. I'm sure there are a lot more, but this has gone way beyond our field. And a lot of people beyond the field of medical who don't understand the requirement, but they have the skills for making it. So making these kind of devices. So they are approaching AI PMR as well. So this is something which is already here. So we need to prepare ourselves and see how we also help in, coming together to make these smart devices safe and all the advantages that our patients need. Because ultimately, whether the device is smart or it is basic, what we want is quality of life, whether you're whatever stage of life you're in, to see a smile on our patients' faces. Thank you. And thank you for your patient listening. So I end my talk.
Thank you so much, Priyanka, for an excellent and creative talk. I'm sure this was very helpful for all the PGs and not only the postgraduate, but for all of us. So the forum is now open for for discussions. Any questions, any comments, you can type in the chat box. And
Thank you.
I
There's a
can,
question. There's a question from Astik Bhatt.
yeah. In recent years, several startups are coming up, such as Create Lab, etc., where a patient take a video from app and a startup 3D print the custom orthosis and sent it to the patient. How effective such startups are in fabricating appropriate fitting orthosis from a video capture, as well as quality and durability of such 3D printed orthosis compared to traditional thermosetting plastic orthosis custom made by a PNO at workshops from in-person patient measurements. So that's the question.
Okay. A very specific question. Now, I don't know the lab, nor do I know what kind of pictures you're taking, but you do need a PNO person because some kind of a mold has to be ready. So it's not only from a picture that you can create a 3D printed orthosis, you need measurements. So you need the patient and you need some kind of a mold needs to be taken, which can be done in a CAD/CAM way or the basic way. And that has to be put in a computer graphic. And it has to be very specific. You cannot remold it like our normal devices. So which one is better? If it's made perfectly, then it will be perfect if it is done the right way. But from a picture, I don't think a perfect device can be made. It has to be, it's very customized. So it needs the patient. And of course, it does need a PNO person at this time because these startups are coming to AI PMR as well. And this is because they don't have the medical or the technical support required to take these captures. They have the device, but they don't know how to translate, how to get both of them together. So I hope I could clear something.
Yeah, this is Creed Labs. He has given a link also to it.
Okay.
So maybe we can see it later on. But yes, that's absolutely right that we need both together if we need the use of technology in the right way. So custom made is always better, and with the PNO, with the CAD/CAM techniques, that's the right way to go. I don't see any other comments, any other questions, but I would like.
There's a comment with Dr. Yadav, sir, about this.
So yeah, this is a very good lecture, and he's congratulating you, Priyanka. Thank you
Thank
so
you so much, sir. Thank you so much.
And maybe our president and secretary would like to say a few comments. We would be happy to hear from them. Dr. Abhishek?
I think it's a very good lecture, Priyanka. I also learned a lot with the new advances we are having in this field. And what's important is the technology has come, and we generally get biased seeing those good pictures or good videos on the internet. But what's important is we should choose what actually help our patients. So many of us stroke patients, they come, they will, my uncle is in the US or in China, they send me a device, can I use it? So there are so many devices has come actually. Same like for hand. There's a static orthosis, there's a functional orthosis, there's a glove, there's a VR system, there's a BCI system. Now patients are buying it themselves at home and started using it. And it's cost prohibitive many times. And it might not help them, but it's a non-functional hand and you're using a FES type of device for them because somebody has sent them from abroad and they expect that hand should start moving after that. So we have to also educate our patients that what is good. Technology is not suitable for everybody. Those who require and can benefit should definitely have it. But we all think as human beings that if there's a machine which open and close the hand, if I use that, any non-function can become functional. So our job also is to tell, you rightly said, what is good for you. You should only have what is good for you. Very important message is that take appropriate aids and appliances and orthotics which can help you. Just buying it because somebody else also has it doesn't make sense because it's very, very customized for a specific patient requirement. Very good talk. Thank you.
Thank you.
Thank you, Dr. Abhishek. Dr. Amit, would you like to add something as a secretary of MEPMR?
Yeah, ma'am. It was a nice presentation, and Priyanka, I feel you have covered almost all parts of it. So that's it from my side, ma'am. Thank you.
Thank you, Amit. So for all of us, all of those who have joined us, thank you so much. And I would like to invite for our next series, which is from electrodiagnostic in PMR, which is from Dr. Manisha, and that will be on in the next March, somewhere around 12th or 26th of we'll send you the link to it. Do we have Asmita? Do we have the slide for that? And in the meantime, Priyanka, this was really very nice, excellent talk. And robotics, they are very well into orthotics also. So the upper limb, lower limb, and spinal orthosis, everything was well cleared, well covered. It's a mammoth task taking all things together, but it was really very good. I'm sure all of us have learned today something, and very good, very many things we have learned from this talk. So I don't think so Asmita has this, but we will definitely send you the next webinar, which is on 12th of March, and which will be on electrodiagnostic. So thank you so much for joining us. Thank you, Priyanka. Thank you, Dr.
Thank
Abhishek.
you, ma'am. Thank you for the topic.
Thank you all the
Learn.
participants for
Thank you.
joining us. We look forward and we'll meet you again virtually on. You can get the recorded. There's a YouTube link is there. It was on YouTube also. We'll just if you can DM me, Lavanya, if you have joined late. So we'll send you the recording. You can DM me and we'll send you. So those who want the recording of the lecture, we can send you. We have to DM me. So okay. So with that note, thank you everyone, and see you on 12th
Yeah.
of March. Yeah, this is
Thank you,
what
ma'am.
we'll be doing the electrodiagnostic from Dr. Manisha. We invite you for our 10th session on 12th of March. Thank you so much, everyone.
Thank you.